Thank you. Thank you. Tonight's topic is the nature of time. And time is one of our most precious commodities, perhaps the most precious commodity. I mean, we enter the world, we're given a certain allotment of time. We don't know how much time we're given. After we exhaust that allotment of time, it's all over. So thank you very much for coming and good night. Now, we have spent countless hours, decades, centuries, pondering the nature of time. And as we'll discuss here tonight, there is a lot we understand about time. But if we even reflect on the starting point, where you would imagine that we would begin our exploration of time, the definition of time, we still are hard-pressed to give that definition. Right? Time certainly has to do with change. That's how we recognize that time has elapsed. But trying to really get at the heart of what time actually is proves extraordinarily difficult. John Wheeler, who I suspect many of you are familiar with that name, one of the great physicists of our age who passed away not too long ago, he famously said that time is nature's way of ensuring that everything doesn't happen all at once. And certainly that is a quality of time, but trying to get at the heart of what it is difficult. So what we're going to do here tonight is we're going to approach this deep question from three different perspectives. We're going to kind of try to triangulate on a deeper appreciation, understanding, intuition about time. So in this first chapter, this first act, if you will, of the discussion, I'm going to focus upon how physics deals with the nature of time. And when I conclude, I'm then going to bring out a guest, a neuroscientist, who's going to give us a way of thinking about time by focusing upon the biological structures that allow us to experience time, the passage of time, and various other qualities that we will discuss. And then in the third part, I'm going to bring out a cognitive scientist who will help us think about time from the perspective of language and culture and allow us to put these perspectives together. And in part 4, we'll have a joint conversation where we'll try to have some of a free-for-all to try to see where we can find places of coincidence, differences, and ultimately, hopefully, give you a richer sense of the nature of time. So to begin, physics of time. What we have done to try to get a handle on time over the course of many centuries is devise ever better ways of measuring the passage of time. Now, how do we do that? How do we measure the passage of time? Well, it's a fairly straightforward procedure. We try to find processes out there in the natural world that are cyclical, that are repetitive. And if the repetition is stable, if it's something that is reliable in the sense that cycle after cycle after cycle, they're all the same, we use those cycles to count how much time has gone by. So, of course, as we're all familiar, in the old days, we began that process by making use of the cyclical notion of the Earth's spinning, and that allowed us to introduce the sundial, right? So as the Earth spins and the position of the sun changes, the shadow that we see here will move around, and in that way, we have a means of measuring the passage of time. Now, that is making use of an astronomical phenomenon, but we can go further and make use of mechanical phenomenon, and the step in that direction can be viewed in this picture here. We consider a pendulum, right? So basic physics that we learned in the 1700s tells us that if we have a situation like this, where we have a mass that is swinging on an arm, basic physics tells us that if you know anything about the length of the arm and the nature of the gravitational acceleration, you can calculate how this is going to swing, and it's regular, and you can use that as a clock. But then, we went further from this, and we recognized that there are certain materials, certain crystals, quartz crystals, that if you apply a voltage to them, they oscillate in a very regular manner, and that gives rise to the kinds of watches that were well known and well used in the last 10, 20, 30, 40 years. But even this is a technology that we can improve upon, and we have improved upon it by making use of atomic clocks, in which, for instance, this is an example where a cesium atom can be excited by bombarding it with laser pulses, and then it itself will pulse. And in fact, we now define the second by counting the number of vibrations of the radiation that comes out of this cesium-133 atomic species. So this is a wonderful progression in the history of trying to measure this thing called time, because the device that I just showed you, atomic clocks, they are so accurate, they're so reliable in their repetitive process, their cyclical process, that some of these devices will lose less than a second in 1 million or 10 million years. So that's kind of amazing, right? When you think about our ability to measure this thing called time, and yet we reflect back on the starting point of the discussion where I said we don't actually know what it is that we are measuring. So it's a curious tension between our stunning ability to measure it, but our lack of full understanding of what it is that we are measuring. But even so, we've gone further beyond simply measuring the passage of time. We've been able to, through certain incredible minds that our species has produced, Albert Einstein in particular, we've gained insight into qualities of time that are counterintuitive. They are not the features of time that we experience. So now I want to turn to 3 qualities of time. One having to do with the rate at which time passes, and this is where Einstein's ideas will come to the fore. And then I'll follow that with a brief discussion of 2 other qualities of time that are within our intuition. The intuition that I think we all have, that time flows, right? I think we all have that sense that time flows. And then the third will be our intuition that the future and the past are radically different. And I'll give you some insight into what physics has to say about that quality of time. And we'll see that actually it is not aligned with our understanding of the basic laws of physics. So for the first quality, the passage of time, I think most of us have an intuition, unless you've studied physics or you read popular books on these ideas, but certainly ingrained in our bones is the sensation that time elapses the same regardless of where you are, how you're moving, the gravitational field that you're experiencing. And Einstein was the first individual to come along and establish that that intuition is just not right. And one way of quickly getting at this insight is to remember that Einstein's special theory of relativity is based upon the idea, experimentally verified, that the speed of light is constant. Speed of light doesn't change. We like things that don't change. They're the things on which we can anchor our understanding. And to make use of that constant nature of the speed of light, we can build a very special kind of clock. Some of you, no doubt, are familiar with this clock. It's called a light clock. It consists of 2 mirrors that are facing each other and a ball of light that bounces between the 2 mirrors. So I think I can show you an example of that here. So how do you make a clock out of this? You simply count the bounces. So tick, tock, and you simply count the ticks and the tocks, and in that way, this becomes a clock. And what I want to do is I want to compare the passage of time on 2 of these light clocks, where I'm going to, in just a moment, set that second clock on the right in motion. When they're sitting side by side, of course, the passage of time on them is absolutely identical. The question that Einstein asked is, if you put that second clock in motion, what will happen? And let me first describe what you'll see in the next little sequence here, but just to sort of orient your thinking, imagine that I have a light clock right here. So this is the bottom mirror, this is the top mirror, and you see the ball of light bouncing up and down between those 2 mirrors. Now, as I walk, right, as I'm walking along, imagine following the beam of light, the ball of light. So it starts down here, and as I'm walking, it's going to hit the upper mirror. From my perspective, the clock's not even moving, so it's certainly going to hit that upper mirror. But the trajectory, therefore, will be to start down here, hit the upper mirror in this location, and as I continue to move, the ball of light will go on a second diagonal trajectory and hit the bottom mirror over here. So as you watch this clock, if I darken the theater and the only thing that you could see was the ball of light, you would see the tick-tocks going tick-tock, tick-tock. And the beautiful thing about that trajectory is that it's longer than the straight up and down trajectory. But the speed of the light is unchanged, and therefore, if the light is traveling a longer distance at the same speed, it's going to take it longer to do it. So the tick-tocks are going to slow down. So let me show you that in this sequence over here. So now I'm going to put that light clock on the right in motion, and watch the trajectory of that photon, that ball of light. And you'll see it follows the double diagonal trajectory, a longer trajectory. Now look at the tick-tocks, 9 versus 8, 10 versus 9. Time is slowing down on the moving clock. And Einstein was the first person to realize that time is not something that's universal in the sense that Isaac Newton thought it was. Time on a clock in motion, from our perspective watching it, ticks off more slowly. And it's not just a light clock. That light clock is representative of the passage of time itself. So if you had sufficiently good resolution to watch the biological processes inside my body as I'm moving right now, they would also be slowing down at exactly the same rate as the slowing down of the tick-tock on that light clock. Time in motion slows down. Now, why don't we know about this? Because we travel at speeds that are very slow compared to the speed of light. How fast is the speed of light? Go around the Earth 7 times in a single second at the speed of light. Since our speed is so slow, we don't realize this intuitively in our bones. Einstein figured this out. Now, he also figured something else out. He figured out that gravity has an impact on the passage of time. This is his general theory of relativity. 1915, he writes down the equations, and he realizes that, in a sense, I'll talk a little metaphorically in order to just get the basic idea across. Gravity, in some sense, pulls not just on matter, it also pulls on time, which means that the stronger the gravitational field that you are in, the stronger gravity pulls on time, slowing down its passage. Stronger gravity, time slows down. It elapses at a slower rate. So just to give you an example of that, we can consider, say, the Empire State Building. Imagine you have a clock of any variety, it doesn't matter, that's sitting on the ground over here, and it's ticking away at a usual rate. But now, let's imagine going way to the top of the Empire State Building where gravity is not quite as strong as on the ground. And the stronger gravity on the ground means that the clock on the ground will tick off slower, and you can begin to see the time difference between them. Now, again, not to scale, right? The time difference would be tiny, right? Billionths of a second. But it's not the size of the time difference that really matters for our attempt to understand the nature of time. It's the fact that time is not the same. It's not universal. It depends not only on how you're moving, it depends on the gravitational field that you are experiencing. Now, having said that, the reason it's so small is because the gravitational pull of the Earth is relatively weak. But if you were to go near the edge of a black hole, where gravity is much stronger, then the time warp associated with being nearer to the black hole versus farther from the black hole could result in a significant time warp, time difference between clocks that are ticking at those different locations. And of course, there have been ingredients, there have been examples in popular culture that have made use of that scientific fact, right? What's the most recent and perhaps most famous film that made use of this fact? Interstellar, right? So in Interstellar, if you recall, there's a black hole, and some of the astronauts go relatively close to that black hole, and that affects their passage of time. And just to remind you, Kip Thorne, who was the science advisor and had the initial idea, I believe, for this film, made sure that everything was as scientifically accurate as it could be. So this is an example where just a few hours, according to Matthew McConaughey, Anne Hathaway, down by the black hole, translates into 23 years up on the mothership. Because time is elapsing so slow in the powerful gravitational pull of a black hole relative to the rate at which time is elapsing elsewhere. And I've known about these ideas now, I don't know, 35, 40 years maybe. They never cease to be utterly stunning because they're so different from what our brains intuitively think about the nature of time. Two other qualities of time that I told you I would talk about, not just the passage of time, but also this intuitive sensation that time flows, right? That time somehow is pulling us from second to second to second in a relentless way that often poetically is described as, say, the flow of a river, the flow of time. And to get a feel for that, here's a sort of rough way of thinking about that. We kind of think of motion in the world as, in some sense, being a series of snapshots. I'm showing them discrete, but you'd really imagine them being continuous. And it's moment after moment after moment, and these snapshots just keep on going forward as time elapses toward the future. And this often gives us the sense that the only thing that's real, right, is the present moment, right? The present moment is what's real, and somehow the past is gone and the future is yet to be. And there's something very curious about that way of thinking about time, because a moment in time represents a quality of time that is its most basic ingredient. Change only is observable by comparing one moment to another moment. A moment itself can't change. By definition, it is the ingredient by which we can see change by comparing one moment to the next. So if we think about the present moment, either in this metaphor of snapshots or an equivalent metaphor that often is used, as sort of a projector, right? So it's as if time is going by, and the only thing that's real is the moment that's illuminated. The now is illuminated by the projector of time, and all of the frames that are before or after the one that's being projected somehow are gone. The ones that have yet to be illuminated, future, those that have already been illuminated are the past. But if you think about this, it's strange, because this is saying that a moment of time is real by virtue of being illuminated. But to be not illuminated, in this way of thinking about things, would be for that moment to be changed. It's as if you're saying that moment exists in two varieties, when it's illuminated and when it's not. But if a moment can't change, then that's an incoherent notion, because that suggests that there are two versions of that moment, the illuminated one and the not illuminated one. And this kind of thinking, when really wedded together with Einstein's relativity, gives a very different way of thinking about time, in which we imagine that every moment is as real as every other moment. It's not just that the present is real and the past is gone, the future is yet to be. Every moment is as real as every other. Past still exists, future exists, present exists. And this is what gave rise to Einstein's own poetic description, where he said, the difference, the distinction between past, present, and future is only an illusion, however persistent. And part of what we'll do in the second part of this discussion is try to get a feel for that distinction between our intuition, past is gone, future yet to be, present is real, and what science, from the point of view of relativity and even just logic, seems to be telling us about the reality of all of time. All right, final quality of time that I will focus upon is our intuitive sense that time has a direction. Time has what we call an arrow, right? We are so familiar with the fact that when you look out at physical happenings in the world, they seem to always unfold in one temporal orientation, right? The canonical examples that we like to use, if you drop an egg, it splatters, but it never unsplatters. You know, if someone dives off a diving board, they go into the water, but you never see somebody jumping out of the water, untumbling, and landing on the diving board. And in fact, you laugh, and that's an important fact, because when you see reverse run films, the reason you laugh is because it's so ludicrous relative to your understanding, your intuition about the nature of time. But here's the amazing fact. When you look at the laws of physics, as currently configured, all laws of physics, when properly interpreted, so I won't go into the nuances of that, but all laws of physics have the quality that they treat the future and the past symmetrically, identically, on equal footing. Which means when we physicists study the laws of motion, any sequence of events that can unfurl in one direction, the reverse sequence is allowed by the laws of physics. And in fact, there's an algorithm for ensuring that if you have, for instance, any physical unfolding, if you want to reverse it, all you need to do is reverse the motions of the particles that are involved. And there's a little clip that I'll show you, which also has a certain temporal quality to it. Sort of shows me as a young man, so I'll sort of disappear for this little bit. But this illustrates this point about the arrow of time actually being reversible.
We all know what will happen if I drop this glass of wine. Now, the idea that this mess could somehow reverse itself and form back into a solid glass filled with wine seems absurd. But according to the laws of physics, this can happen. All I need to do is reverse the velocities of everything.
Every piece of glass, every drop of wine, every molecule and atom in the liquid, glass, table, and air. Just reverse all their velocities.
And voila!
If only we could reverse time as easy as that. But the point is, here is a very basic quality of experience, that things seem to only unfold in one orientation. We only ever see things unfold in one orientation, but that's really an environmental effect. It's really the fact that we can't reverse all those velocities as I did in the little clip there, simply because it's too hard to do. But if we could, the laws of physics say that things would run in reverse. So this gives some feel of the disjuncture between our intuition, both for the passage of time with special relativity, moving bodies, general relativity with gravity, our sensation that time flows, and our sense that time has an arrow. Our intuition is sort of at loggerheads with these fundamental qualities of time, and we're going to explore the tension between what we understand about time from physics and our perception of time with some of the world's experts that can give us some insight into the nature of that disjuncture. So to do that, let's bring out a neuroscientist from the Brain Research Institute and the Integrative Center for Learning and Memory at UCLA. He's a leading researcher on how the brain tells time and neurocomputation. Please welcome to the stage Dean Buonomano.
Thank you, John.
Welcome. All right, so you saw in that discussion there, and you already know from your own knowledge of the physics side of this discussion, that there is this tension between what physics has found and our intuition about how the world works. And I gather part of the explanation there must lie in the fact that our brains evolved in order to survive, and to survive you don't have to know about these curiosities about the nature of time. But can you take us into your understanding of how the brain processes time, how it keeps time?
So I think there's a big difference here between physicists and neuroscientists, in that neuroscientists tend to be implicitly accept the notion that only the present is real. and the future is not yet real, and the past is no longer real. And that's because the brain is an inherently temporal organ. In many ways, if we can say that the brain has a main function, its main function is to store information about the past in order to predict and prepare for the future by acting on the present. So the fact that we talk about memory and future means that we're sort of assuming that we have the ability to change the future. And that's the currency of evolution. The degree to which I can anticipate what's going to happen gives me a powerful evolutionary advantage. So starting from that distinction, then the question is, okay, how does the brain do that?
Right.
And then the brain learns. We form memories. We store information of the past. And the implicit idea there is that that past no longer exists except within our neural circuits. And then we predict the future. And to predict the future, you need to tell time. It's not sufficient for your weatherman to say, it's going to rain. It's helpful if they tell you it's going to rain tomorrow or the day after. So the question of how the brain tells time is key. And Brian...
Is there a structure in the brain that's specifically oriented toward keeping time?
So that was one theory decades ago, that maybe you have some central clock in your brain, sort of like a computer has a clock chip that sort of controls all the temporal processing done by the computer. So that was one theory. But the point is really that because timing is so important for everything we do, right now, you are paying attention to the timing in my speech, but you're also paying attention to the time on that clock over there.
Oh, you saw me glance over there.
to time the pace of this. So the brain is attempting to predict what's going to happen by telling time. And let me give you, so for example, right now, your brain is unconsciously attempting to predict what is about to happen. By pausing my speech, I created a temporal prediction error in your brain because you were unconsciously attempting to predict what was going to happen. It didn't happen. So then you became consciously aware of, and Brian started thinking, uh-oh, he forgot what he was going to say. Or the audience said, man, this guy's boring. And another thing happens there, Brian, is because it was sort of an awkward silence, you probably became more aware of the passage of time. And this is the fundamental point you just approached, right? Which is the flow of time, the notion that time is not a static frame in the movie, but flowing. And that's where, as you alluded to, the clash comes between physics and neuroscience. And neuroscientists tend to blame physicists for not understanding time, and the neuroscientists and the physicists hope that the neuroscientists will explain where this illusion comes from. And I think that will be an issue that maybe we can talk about shortly. But regarding how the brain tells time, you mentioned that throughout human civilization, we've been inventing more and more powerful ways to tell time. And today, we don't measure anything as well as we measure time. So indeed, we measure space by telling time. A meter is defined by how far light goes in a specific period of time. So, and all these man-made clocks tend to rely on a fairly simple conceptual concept, right, which Brian mentioned, which is just the counting of these oscillations, whether the oscillation of a pendulum, oscillation of a quartz crystal, or oscillation of the vibrations of a cesium atom. The brain, the timers or the clocks created by the brain are fundamentally different from those that are within the brain. So the brain does not tell time by counting the ticks of an oscillator. So yes, there are oscillators. For example, your circadian clock is an oscillator that tells you when to get up and when to eat. But the neurons in your brain that are oscillating, they have no idea of how many times they have oscillated. So something that Brian didn't quite mention was that a key feature of using a quartz crystal is something has to count the ticks.
Yeah.
And the same thing with an atomic clock. So while the circadian clock neurons are oscillating, they haven't a clue if they've oscillated 1,000 times or 10,000 times or 100,000 times. So the other thing amazing about man-made clocks is the same atomic clock can count picoseconds, microseconds, milliseconds, seconds, days, years, and so forth. So the brain is also able to tell time across vast scales, but they're fundamentally different mechanisms. So your circadian clock does not have a second hand. The timers or the circuits in your brain that allow you to pick up the pause in my speech have a second hand but don't have an hour hand. So the brain has many, many clocks. So the answer to your question is no. There's not a centralized clock that tells time across scales and solves all our temporal problems.
And I mean, from an evolutionary perspective, it's clear that having the capacity to keep track of various temporal durations has survival value, right? I mean, internal processes that need to coordinate the production of proteins and different processes have to happen in a certain rhythm. You know, we have to know to get up. You know, if we didn't get up, that would be the end of it all. So with this being the case, is it true that, say, across all animals, they keep track of time in the same way? Or are we different from other members of the animal kingdom?
We inherited a lot of the clocks of our mammalian ancestors. So the ability to tell time, the circadian clock, is very similar. You don't even have to have a brain to have a circadian clock. So bacteria and plants have circadian clocks. And by the way, something you mentioned is a very good point, is that we call it a circadian clock, but even the circadian clock is really a prediction mechanism. Because as you said, it's not about necessarily waking up. It's about preparing the body to engage the correct proteins and hormones. So it's more of a prediction device than an actual clock. And animals have ways to tell time on the millisecond scale too. So that's very, very similar across species. What's different is our ability to conceptualize time. So humans and animals different. So if you look at human evolution, all animals try to predict what's about to happen. You know, the simple act of throwing something towards you is a prediction act that you're going to catch it or something. So you have to look into the future, or a cat that's jumping up in the air to catch a bird, right? It's predicting the future. Humans did this amazing thing that they went from predicting the future to making the future. So the simple act of planting a seed to say, okay, instead of searching for food, I'm going to make the food, and that food will come to me. So this is what we call mental time travel. So somewhere along the lines, our ancestors became able to engage in the ability to travel short or long periods of time in the past and in the future. And this
Totally in their heads.
Totally in our heads. So,
Yeah.
so the fact of the matter is, as a physicist, I don't know what your position on time travel is, but you probably agree that it's not a practical matter. So the best time machine we have is our brain, and our ability to simulate. You and I simulated in our brain being here to prepare for tonight. It might not look that way, but we did. And so that ability to engage in mental time travel, to plant the seed and reap the products of that, is beyond the cognitive ability of as far as we know, of all other animals.
And what about the phenomenon that I mentioned that is probably the most familiar quality, intuitive quality of time, that sensation that all these moments are somehow stitching together? Yeah. Is there evidence that we have a minimal amount of time that will constitute something that we're aware of?
Yeah.
And I'm assuming that there is for that. And given that, can you tell us anything about the process in the brain that stitches together all of those moments into something that feels continuous?
No.
Thank you.
So there's two aspects to that question. So first, there's what's happening unconsciously. So unconsciously, our ability to pick up differences in small amounts of time is actually quite astounding, given that neurons are so slow. For example, sound localization from my right ear to my left ear takes maybe 100 microseconds, and you can easily pick that up. But that's unconscious. Mm-hmm. Now, at the conscious level, the question of if there's a quantal time is a bit different. And there's not really, but it's very flexible. So I think you're referring to the question of our conscious perception of time. And that's a much deeper question. So first place, of course, there's a delay. So when we process each other's speech, we're in a sense living in the past a bit because it takes any computational device, whether it's a computer or the brain, some finite amount of time to process that information. But then that's natural, so that's just a consequence of physics. Now, there's a deeper question here, which is, when do we become conscious of something? And although you might think that you're perceiving my speech as one continuous flow of the river, it's really not. That's a bit of a meta-illusion or a mental construct, in that your brain processes things in chunks and then stitches them together. But the amount of that stitch is actually variable. It's not fixed. Let me try to give you an example by saying 2 sentences here. The mouse pad and computer are new. Okay, second sentence. The mouse was eaten by the cat. Okay? So I think, hopefully, you understood both sentences had the word mouse, and they had different meanings. But you only knew the meaning by the word that came after.
Right, yeah.
Okay, so if I say the mouse pad and computer are new, you don't know what I was going to say until what comes after. But most of you, I'm guessing, didn't edit in time backwards to readjust your interpretation of the mouse. I don't know. I'm assuming you didn't. So clearly your brain is chunking things in time. So the way to think about this is your unconscious brain is continuously processing information in a more or less linear manner. But consciousness, which is really a small fraction of what goes on in our brain, is generated once the unconscious brain arrives at some reasonable narrative, some reasonable story of what's happening in the external world, and generates to consciousness. Sometimes that, most of the time, fortunately, that story is correlated with what's in the real world. Sometimes it's not, and that's an illusion or hallucination.
Now, speaking of illusions or hallucination, you know, I've had friends tell me about psychoactive drugs. And these friends have described their experiences so vividly that I almost feel like I've had those experiences. So I'm wondering, they describe situations in which the effect of the psychoactive drug was to radically change their perception of time in a variety of different ways. So clearly, you know, a chemical flowing through the brain can radically change everything that you're describing as the normal neurological functioning.
And you'll be glad to know that you can feel this without having to do as your friends do, take those drugs, just by engaging in something that's really boring, or an exciting near-death experiment or experience, or jumping from a plane if you don't want to do the drugs. And then you're using your own drugs, literally, the neuromodulators that do that. So there's, again, 2 levels to this question. What's happening at this unconscious circuitry level? And neuromodulators and the chemistry in your brain, whether they're altered by pharmacological compounds or not, modulate the neural circuits within our brain. So they can accelerate the processing of the neural dynamics or not, changing our perception of time. So if we accelerate the neural dynamics through some pharmacological means, then our internal clock is going faster, and the external, which means that, in relatively speaking, the external clock is going slower, so we are left with the perception that time is slowing down. Now, that doesn't really explain the consciousness, which I think is what your friends were referring to. The conscious perception there. And that is a much deeper question because it's tied to consciousness. And in a way, I think it's the wrong question. And let me, if you give me some leeway here, I'm going to make an analogy. So there's an illusion about body awareness. And the illusion is phantom limbs or phantom pain, right? So people who don't have an arm often feel that arm as it's still there. And this is very paradoxical and strange for us who have never felt it. How can you feel something that's not there? And the reason you can is we know that the feeling of the body is not happening in the body, it's happening in the brain. So if I'm to hurt my finger, my brain is projecting that pain out here. So the mystery of phantom limbs is not the phantom limb, it's our normal limbs. So it's misleading to ask what causes phantom limbs. The correct question is what causes our normal body perception. My point is that the same is true in time. So looking at the distortions of time is really the least of the mysterious questions. The more mysterious question is what our normal perception of time is. And that's inextricably linked with consciousness, and it's a difficult question.
So given that, a thought that's always in the back of my mind, a somewhat disturbing thought, actually, is that we as physicists have spent a lot of energy and effort trying to work out the qualities of time, and I described some of them in part one of the program here tonight. Of course, everything that we figure out with the same gloppy gray structure inside of our heads, which perhaps for evolutionary reasons gives us a certain kind of temporal experience of reality. Could it be the case that a different architecture might have led to a radically different way of experiencing time and a different way of thinking about time out there in the real world?
Absolutely, and I think, but here's, as you said, so the brain evolved to survive in a world governed by the laws of physics, right? So this is a pretty stringent test.
Yes. But the laws of physics acting out in a very limited domain of experience.
So our intuitions about quantum mechanics are horrible, and our intuitions about general relativity are horrible, because those domains aren't particularly important for survival. Time is, though, right? So time is not a property that's limited to quantum mechanics or general relativity. It's very mesoscopic. So I would argue that we have to take very seriously our intuitions about the past not being real, the present being real, and the future also not being real yet. So, because I struggle to see
But
why.
let me ask you a question. I don't mean to interrupt, but that's a key point right there between the physics and the biological perspective. Because when I think about biology and the brain, I always think, hey, so this thing had one goal, which was to survive long enough so that the bearer would reach reproductive maturity and pass on the genes to the next generation. And my view has long been that that's radically different goal than figuring out the true nature of reality. In fact, moreover, my view has long been that those of our forebears who may have been prescient and knew about the strangeness of time that came, say, from Einstein, when they were out there on the plains thinking about time dilation and general relativity, they got eaten. They weren't focused on the goal, which was survival. And so when you say we have to take seriously that sort of the past is gone and the future's yet to be, I wonder why you say that.
Yeah. So I say that because unlike our forebears that were thinking about quantum mechanics, they would be eaten. And fortunately, and same with general relativity, fortunately Einstein was not eaten. But with time, it is critical for survival, because as I said, the brain is a device that stores information about the past, that's memory, in order to predict the future, and that's what you're doing. So I think the question that we have to try to resolve is whether the temporal component of our conscious experience is real or not. Let me try to give you an analogy, another one, in terms of color. Okay.
Yeah, sure.
We know that in physics, color doesn't really exist.
Right.
What we have is wavelength of electromagnetic radiation. The color is evolution's hack to build a spectrometer. And it's imperfect, but it's pretty damn good, right? So Newton used his perception of color to make very valid inferences about the physics of light. Now, I think by the same reason, color is adaptive because it tells us it's correlated with the real world. I think our feeling of the flow of time wouldn't have evolved if it weren't correlated with the real world. from an evolutionary perspective. Now, my question to you, Brian, is the following. If an omniscient being came down to you personally and assured you that the past, present, and future are different, that the present is in some sense more real than the future or past. Obviously, we know that absolute present doesn't exist because that's been well tested, because we know clocks change at different speeds. But that doesn't really say that the present is not fundamentally different from the past or future. So if that being came to you and said that, would you have to go in there and rewrite any of the laws of physics, or could you still use the same laws?
Well, it's a good question, and actually it's a relevant one, because I have been visited by that omniscient being.
Was this with your friends?
No, yeah. So here's my view. My view is that much of what we're talking about tonight is absolutely vital from a human scale perspective, because we're beings that live in the world, and we want to have a deeper understanding of this quality that is with us every moment of every day. There's barely a sentence that I can utter that doesn't have a temporal quality in it. So it's so vital to everything that we do that we want to understand it more deeply. From the standpoint of fundamental physics, much of what we're talking about just doesn't matter. If you look at the equations of relativity or quantum mechanics, you can use those equations to make predictions about what will happen in various experiments without having to commit to whether the past is gone or the future is yet to be. So it's an interesting state of affairs where I don't think that I would need to rewrite the laws of physics at all, given this information, assuming that it was true, because ultimately this is a layer of human interpretation that's sitting upon the more fundamental understanding. Now, that's not to say that our current understanding down here is the final story. I don't think that it is. My guess is that there will come a point, and it's starting to bubble up right now in fundamental physics, where we'll recognize that time is not as basic to the laws as we once thought. There's evidence to suggest, and this is things coming from quantum gravity and string theory, which are certainly on the edge of speculation, but there is reason to suspect that time is something that emerges from a more fundamental starting point. The analogy that I like to use is temperature. So we all know what it means when something's hot or something's cold, right? Totally intuitive. We learned many decades ago that there's a more fundamental underpinning to that, which is when something's hot, its molecules are moving fast. When it's cold, its molecules are moving slow. And temperature simply is a measure of that average kinetic motion. So that says that temperature emerges from a more basic starting point having to do with the motion of atoms. Now, my belief, and this is not iconic to me, there are many in my field who feel the same way, that there is an analogous notion of atoms, but not for matter, but for time. That there's some more basic fundamental ingredient that when it is in the right configuration, time emerges. But when it's not in that configuration, there isn't even a conception of time. Yeah. And that's why these ideas are sort of very high level. However much they matter to us as human beings, I don't think they matter to the fundamental laws of physics.
So to me, your answer in which you won't have to rewrite the current laws of physics is very interesting in that maybe that gives us room for the present being different from the future and the past, and saying that it's an interpretation. Let me just say one thing. So in the end, humans, and this might be a good transition to bring in Lera, in the end, humans are literally just unusually smart apes. We really have no right to think that we should understand the laws of the universe. What's surprising is that we've gotten as far as we can, given that the brain has many glitches, many limitations, many bugs. The most powerful debugging tool that we have, I think, is mathematics.
Yeah.
And once some genius conjures up these sets of equations, the rest of us can put in numbers to those equations and predict what's happening in the external world. Now, once you're able to do that, you have the power of the science underlying it. But once we start interpreting them, then the word interpret means it's being filtered through your brain. So I would pose to you the possibility that given how the brain was built, evolved, we have a bias to interpret those equations in the context of the spatialization of time, because that's the best way to make sense of those equations, given the very ephemeral, the very limited computational device we have at our disposal to interpret those equations.
Yes. Yeah, and I would agree with that. And that is a great point for us to transition to the language interpretive quality that we humans impose on time. So from one intelligent ape to another, I thank you for the conversation. We'll bring you out in just a moment after this.
Thank you,
Dean Buonomano.
Thank you.
All right, let's now bring out a cognitive scientist at the University of California, San Diego, whose research focuses on the relationship between mind, world, and language. Named one of 25 visionaries changing the world by the Udny Reader, please welcome Lera Boroditsky. Thank you for being here.
Thanks for having me.
So we just finished that discussion on the note of mathematics as a language.
All, yeah.
Well, we didn't quite solve it all. That's why you're here. So we were thinking about mathematics as a language, but one that perhaps gives us deeper insight into the nature of reality than natural language, which is our attempt to describe in a way that we can make intuitive sense of the world around us. So when it comes to language, and the language that we use to describe everything, not just time itself, where do we stand in understanding where language came from, the origin of language? We know a lot, about the origin of the universe. I can tell you all sorts of details about that. How have you guys done in figuring out the origin of language?
Well, we're still waiting for the time machine that you were supposed to deliver.
That
would really help.
Yeah.
The reason I say that is that language is a soft historical artifact.
Yeah.
It doesn't leave a trace in the fossil record. So it's actually very, very hard to know a lot of solid facts about the history of language after you go back more than, say, 10,000 years.
Right.
So the start of written language, of course, helps, but we only have written records for a small handful in only a few thousand years. And then beyond that, we can make some inferences by the patterns of interrelatedness between languages. But once you get past a few thousand years, we're really making a lot of conjectures.
Right.
So the time machine would be very handy.
Okay, we will keep that in mind.
My order is in.
It's in, absolutely. Yeah. You'll be the first to get one.
Excellent.
So when we think about language, though, I think many of us, well, maybe I speak for myself, language is this means of abstracting our experience. I mean, when I think about, I've got a couple dogs at home, smart dogs, but they more or less live in the moment. I mean, they do know certain things about, when it's mealtime, and they know to behave in certain ways when they want to go out and so forth. But for the most part, the way that they live is in the moment. Yet I and everybody else, through the power of language, seem to be able to rise above the moment. Mm-hmm. And that's when we can begin to think about the past and imagine the future. So in that sense, is language the rubric within which our intuition of time happens, or is it the reverse? Is it our experience of time that guides the language that we use to articulate it?
Well, certainly humans are able to entertain ideas about the deep past and the deep future that are unlikely to happen in other creatures, but lots of creatures can predict things that will happen, can maybe even reminisce or replay experiences.
Really? Reminisce?
Well, certainly if you make a rat run a maze, for example, and then measure the activity in the hippocampus of that rat as it's running the maze, and then measure it while the rat is sleeping, some of the very same patterns of activity that are specific to that geometric pattern of the maze will be being replayed. So if you want to interpret that as a reminiscence or a dreaming about...
Right. And do you think that's stretching our usual notion of reminisce a little bit, or do you seriously think that the rat's there, wow, that was fun, that last run through the maze. We'd love to do that again.
Well, I think all of these words that we use for mental processes are slightly metaphorical, right?
Yeah,
the brain is not necessarily broken down into words we have in English for things like reminisce or predict. there are going to be lots and lots of different neural processes that won't necessarily be exactly the set of words we happen to have in English right now.
So how does language impact the way that we mentalize time? I mean, has this been studied to figure out the interrelationship between the two?
Yeah, so well, let's start with the simple observation is that there are about 7,000 different languages in the world, and each one of them offers a different perspective, not just on time, but on all other aspects of our experience of reality. And with things like time, there's a particularly interesting conundrum to solve, because on the one hand, time does form the very fabric of our experience. We can't experience anything outside of time. So it's fundamental, it's core. But on the other hand, we don't have any sensors for time directly, right? So we can't smell time, we can't touch time, we can't see time, we can't hear time. And yet we construct this notion of time that we all then agree to live with. So how do we create this abstract entity in our minds? And worse, how do we create ideas that go beyond what's physically possible or experienceable? Like, how do we come up with a notion like time travel? That's a very crazy thing for humans to come up with, because as we walk around the world, we have physical sensors in our skin, we get photons in our eyeballs, we get pressure waves in our ears, we squeeze our toes and bend our knees just in the right amount to defy gravity, and then we end up with ideas about quantum mechanics and time travel and goals and love and principles, all of these fancy ideas that, how do they come from that physical experience?
Good. That's a very good question.
So this is where I think we can turn to language, because language is a wonderful way of taking some of the more basic experiences that we have, things that come from the senses, things that come from what we can observe about the physical world, and then building on those things. So in language, you can recombine things endlessly, and you can make lots of analogies and build on those analogies. And so the fact that language allows us to endlessly recombine and create new ideas, new thoughts, just by taking old elements and putting them together in these different forms, allows us then to go beyond what we can experience.
But do different languages, which have different, I mean, there's a lot of similarity between those 7,000 languages, but there are, of course, distinctions, significant distinctions.
Yeah.
Do those differences show up in the way that different cultures approach time or think about time?
Yeah, there actually are huge, fascinating differences in how people think about time. And it's, I'll give you a couple of examples, but let me start with this. A very simple difference is the direction in which you read and write changes in which direction you think time flows. So for a normal English speaker, time flows from left to right, where the past is laid out on the left, the future is on the right. If you see someone gesturing, for example, you'll see this. If you read from right to left, then time goes in the opposite direction. So if you ask Hebrew speakers to lay out pictures, or Arabic speakers, they'll lay them out in the opposite direction. And this is such a pervasive experience for us that we imagine things unfolding in our minds in a particular direction. If you just ask people, suppose I tell you, Bill is giving flowers to Mary. Draw me a picture that shows that. People who read from left to right, like English speakers, will draw Bill on the left and Mary on the right, whereas people who read from right to left will draw Bill on the right and Mary on the left, go in the other direction. And not only is it just that we imagine these things, but it's so deeply built into our brain that if you damage the part of the brain that represents, for example, the left side of space, it also disrupts the imagined left side of time. Right? Of course, time doesn't have a left side. You're a physicist, you know that. So there's no such thing as a left side of time, but in our minds there is, and it is.
So you mean that if I'm an English speaker, and the left for me represents the past, I suspect for many others. You're saying if there is damage to my brain which impacts that side, it'll be the past that's impacted. Whereas if I Hebrew is my native language, it would be the future?
Yes, exactly. So there's a very common kind of stroke that you can have in the right parietal lobe that causes left neglect. So patients with this kind of stroke might only be able to read words on the right side of a page. They might only eat food on the right side of their plate and complain they're still hungry, and you can turn the plate for them. They might only put makeup on one side of their face or shave one side of their face. So they've lost the ability to pay attention to the left side of their world, of their visual world. And if you tell them about events that are associated with the past, like 10 years ago, Dean liked eating strawberries, but in 10 years, he will like eating cherries. And then later, I test your memory for these events. Patients who read from left to right will have a hard time remembering things that were associated with the past. But ones who read in the other direction will have a harder time remembering things associated with the future.
So this is an example implicitly in which space is being used to represent time. And, you know, as a physicist in the mold of Einstein's insights, that warms my heart because we learn that space and time are really knitted together into the fabric of space-time. So this is a resonant idea. But is it the case that every culture, every language uses a spatial metaphor to describe time, or are there other ways of doing it?
There are a few languages people have described that don't heavily rely on, that don't heavily rely on spatial metaphor.
Okay.
And then sometimes you get into semantics about what really is spatial. So like if you say the future is in the heart and the past is in the head, is that still spatial because those are actually two different locations, or is it a different kind of organization?
Yeah, I mean, it feels different at first blush.
But going back to your thought about how space and time seem to be intricately linked in the mind, they may be more linked in the mind than they should be in human minds. So let me give you an example. Suppose I ask you, next Wednesday's meeting has been moved forward 2 days. What day is the meeting now that it's been rescheduled?
It's either Friday or Monday. And,
Who thinks Friday? Okay, who thinks Monday? Okay, well, that's about normal. You guys can discuss later.
But that is it? I mean, it's sort of a 50-50-ish split
for English speakers, it's about 50-50, depends on a lot of variables. But here's why people have this disagreement.
Yeah.
We have two different ways of talking about time in English. In one way, we talk about ourselves as moving forward in time. So we say, we're approaching the deadline. We're coming up on the holidays.
Yes.
In the other one, time is moving towards us and we're stationary. So the deadline is approaching. The holidays are coming up. Now, if you think of yourself as moving forward in time, then moving the meeting forward is in your direction of motion from Wednesday to Friday. But if you think of time as moving, then the meeting should move forward in the direction of time from Wednesday to Monday.
So if you have a really overinflated ego, you would have said Friday. Is that, you know, because it's your, everything, is that roughly the...
We haven't done that experiment,
yeah.
But we can. I mean, all our participants are very humble.
Right.
But what you can do is you can get people to think of themselves moving in space. So if I get you to imagine moving towards a target, or I get you to imagine something physically coming towards you, your answer to the next Wednesday's meeting question will change. So if you're
saying if you kind of prime my thinking by suggesting something.
Yeah, so if I say, imagine yourself scooting in an office chair towards a goal, or imagine using a rope to bring that office chair to you. If you've just been imagining yourself scooting, you're more likely to say Friday. If you've been drawing the chair towards you, you're more likely to say Monday. Now here's why I say space and time might be too related in the mind for this, because if I'm approaching the deadline or the deadline is approaching me, those really should be the same thing. Those shouldn't physically be different. And yet our brains are treating them as different. In space, they're different because there's a fixed ground against which we're moving. So if I'm approaching you or you're approaching me, we can tell the difference between those because there's something else that's staying fixed.
This is relativity. But anyway, go ahead.
But then in time, if it's really one-dimensional, you shouldn't have this quality. But people seem to be treating time as if it's actually more dimensional than that. So they're treating these two scenarios of me approaching the deadline as opposed to the deadline approaching me as being actually different psychologically.
Is it the case that effectively all languages, if they do invoke a spatial metaphor for time, is it always a straight line? I mean, that's, again, Einstein's insight was to loosen that up significantly. Are there any cultures that have loosened it up for whatever reason?
Yeah, so there are lots of variations. So, of course, we have circles that time travels in, both in American culture, but also other languages use the circles much more. Of course, when you're studying how people think about time, if you find what looks like a linear representation, you don't know if that's just a small part of a circle that you're looking at, right? So it's possible that there are even larger circles that are in there that you're not seeing. But some people actually have broken the idea that there should be a straight line at all, that you could just have a bent line. Let me set this up. There's some places where time doesn't travel with respect to the body. So I've given you examples where time can go from left to right or right to left. But there's some places that people don't use words like left and right at all. And instead, everything happens in north, south, east, west, or some kind of cardinal direction space.
I mean, so a fixed orientation relative to the Earth as opposed to relative to the orientation of the human body.
Yes, and so in languages...
I wouldn't do well in that civilization.
Well, you would learn.
I guess, probably.
In fact, kids in these cultures go through really awesome training where their parents will say, oh, do you know where grandmother's house is? And the kid might say, yes, it's over there. And the parent will say, no, it's over there. And you get this kind of micro-correction so that you can get quite precise because that's what's expected of you. In fact, in some languages like this, even your body parts would be described using cardinal directions. So you might say, oh, there's a little speck on your southwest shoe. And so if you...
Are you serious?
Yes. And then if you swivel like in this chair like you're not supposed to, then of course it would no longer be your southwest shoe, it would change. So imagine doing the hokey pokey in a language like that. There would be a lot of mental gymnastics. And so for folks who think of themselves in space that way, instead of thinking in terms of left and right, instead thinking in terms of cardinal directions all the time, what we found is they organize time also in cardinal directions. So for example, one group that I studied, the Kuuk-Thaayorre, this is an Aboriginal group in Australia, instead of making time go left to right or right to left, they make it go from east to west. So if you sit someone facing south, they'll organize things from left to right.
And obviously this is related to the rising and setting of sun, or that must be the argument.
The sun is a really good organizing principle. But it's not the only one that people use. So other places, you might live on a hill, and so then time might go uphill. Other places...
I mean, there are cultures in which...
Yes. There's a culture in Mexico that's Saltal, where time goes uphill.
I see.
There's a culture in Papua New Guinea where time goes downriver. And there's one that we know of in Papua New Guinea, this is work by Rafael Nunez, where time, this is the Yupno, time flows into the village at one angle, and then it takes a turn and flows out of the village at another angle. And this has to do with the location of the source and the mouth of the Yupno River. So these are important locations for them, and so time there follows the exact topography of the region, rather than going in a straight line or following some kind of other fundamental
and how does that manifest? I mean, like in everyday conversation, if you're like referring to the past, you're like going, you know, and the future. I mean, are you actually making use of these oblique angles in your articulation of
In fact,
past and future?
that's exactly how he measured it. He asked people to tell stories about things that happened in the past or things that they're planning to do in the future, and he could measure the spontaneous gestures that people made as they were talking about their plans. Though very often, if you speak a language that has absolute directions like this, you are unlikely to gesture for things that are not space, because your spatial gestures actually mean those things. So when I gesture in English, if I say, oh, I used to live in San Francisco, or I'm going to my grandmother's house, these gestures don't go anywhere.
Sure.
Like you can't follow these gestures and get to any location, right? Whereas in these cultures, you can follow those gestures. In fact, I had one conversation with a fellow in Temporal where I asked him what he was doing the next day, and he said, oh, I'm going fishing. And as soon as he said that, he realized he'd just given away the location of a secret fishing spot. And so then he started saying, you know, fishing. He had to kind of blur the location a little bit.
So in these cultures, when one goes indoors, you're keeping track of your bodily orientation relative to the grid, the east-west, north-south grid?
Yes. So in these particular communities, people keep track of it when they're indoors, also when they're in unfamiliar locations. It's just a matter of keeping a map. It's usually a top-down kind of bird's eye view map, and keeping it rotating in your mind. And this actually had this experience. I was there for a little while, and I was really trying to stay oriented because people treat you like you're a little bit stupid if you're not oriented, rightfully so.
Yeah, right. Yeah.
And then one day I was walking along. It was a hot day, and I was frustrated about something. And I just noticed this window pop up in my mind. That was the landscape seen from above, and I was a little red dot traversing this landscape. And then as I turned, the thing rotated in my mind's eye so that it would stay fixed on the landscape. And as soon as I saw that, and it just happened automatically, as soon as I saw that, I thought, that makes it trivial. Now I have this extra little widget in my mind that I can just read off
sort
of.
of a mental compass that's there with you.
And I then confessed this to someone kind of shyly there. I said, this weird thing happened. I saw this, and they just kind of said, well, of course. How else would you do it?
So I have no idea whether any of these studies have been done, but if you take a child who's grown up in this environment where they're thinking about time rather different from the way different spatial metaphor and so on, when they go and learn, Newtonian physics or relativistic physics, does this impact the way that they absorb these ideas, or do they just sort of leave that behind and become the way, start to think the way that someone in this culture would think about time?
Well, I feel like relativistic physics has zero relationship to how people in this culture think about time. I mean, you teach undergrads. Do they come in with intuitions that seem to align with relativistic physics?
Well, it's a good point.
I feel like everything that physics tells us about the structure of the world is complete. Like, physics tells me that this is almost all empty space, and yet that would be extremely inconvenient for me to believe if I wanted to not walk into it. Right.
Absolutely.
About everything you could tell me about the environment.
So I agree that it's
we're
all
in.
counterintuitive, which is in many ways the appeal to somebody like me, because I'm thrilled by having my preconceptions of the world smacked around. I mean, there's nothing to me that's more exciting than to learn that everything that I long thought about the world is wrong. That's a glorious moment for me. But what does happen is you acclimate your intuition to bring it as close as it can be to these strange ideas. For instance, the ideas that we started the discussion this evening with, the time dilation and motion and gravity and so forth. And my intuition about time is now sort of grafted on to this deeper understanding. So there's this interplay between intuition and mathematical understanding. So there is a deep connection between them. So it does raise the question, if my starting point was radically different because of a different cultural perspective, a different linguistic orientation, would I think about these strange ideas differently?
I think you would be coming from a different starting point, and I think there are many different ways to come from a different starting point. And so it may be that it would take you longer. It may be that you would arrive at a somewhat different understanding. I'm not sure that we could know that any two Western physicists have actually the same understanding of relativity.
True. Yeah.
Probably a lot of different representations and schemas and ways of framing and formulating happen in the mind, where someone might have a more visual representation, someone else might be more symbolic or formulaic.
Yep.
And so that's maybe part of the reason that some people come to insights sooner or later.
Yep.
So, but you're bringing up this really wonderful point about the diversity of human thought, just how many different ways we have of conceiving of even our basic physical facts around us, and then how we use, starting from that incredible diversity, how we then use to try to rise up higher and higher.
Right. So one final question before we bring Dean back on. A lot of our conversation has focused on language as a rubric for understanding and organization. And, you know, I wonder, I mean, Wittgenstein had this view that language sort of set the limits. I forget the exact quote, but it's something like, the limits of my language set the limits of my world. Something close to that. Now, there's an alternate view, which is closer to my own perspective, which is that there's a whole body of understanding that goes beyond language. I feel like I know certain qualities of the world that I don't articulate, that I don't put into linguistic form. Do you share that, or is someone who sort of lives in this world of language as the architect's the rubric, do you feel that is the limit of the world, or that the world far transcends this one little way of describing things?
Well, let me say two things. One is there's certainly some things that are more effable than others, right?
Yeah.
And Wittgenstein gives this example of if I ask you, how tall is Mount Kilimanjaro? If you happen to know the answer, that's an easy answer to give in language. Language is good for that sort of thing. But if I ask you, what is the sound of a clarinet like? It's a lot harder to give that answer in language. And so the question is that inherently a property of language, or could we somehow F the ineffable, maybe develop a better vocabulary?
Right.
And the other thing you said is, are the limits of our world the limits of this small thing called language? Language to me is not a small thing, it's an infinite thing, right? So because from a finite set of elements, you're able to recombine and make infinite combinations. So because it has this compositional quality, it actually allows us to constantly go beyond what we can imagine. So coming back to this idea of time travel, how do these physical soup of bones and meat that we are inside a skin shell, how do we come up with an idea like time travel? Well, here's a simple way that language could help. If you talk about time as a path that you can travel, so if you can say things like, we're approaching the deadline. As soon as you have that metaphor, that analogy in place, time is a path I can travel. You say, well, wait a second, paths I can travel in any direction, whatever speed I want. So why can't I think about myself now traveling in time, right? And it just takes that little analogy to set you off to now have a thought that goes far beyond what you can physically experience in your lifetime.
So hold on to that thought, because that's exactly where I'd like to go. But let's bring Dean back out for a final three-way conversation here. So, it's an idea that, of course, is a trope of science fiction, but it's something that I think we all have a deep emotional connection to. So from the physics standpoint, maybe it wasn't completely clear, but it's perhaps worth being completely straightforward about it. The qualities of time that I described at the outset do allow for time travel. Time travel is part and parcel of the laws of physics as we understand it. Now, I should qualify that by saying time travel to the future is what we fully understand. So, if I wanted to travel 1 million years into the future, there are two ways that Einstein told me I can do it. Go hang out near a black hole sufficiently long time, come back, perhaps a year goes by for me, 1 million years go by on planet Earth, or get into a rocket ship, head out into space for 6 months at an appropriate speed, near the speed of light, turn around and come back, get off of that ship, I will have aged 1 year, 1 million years will have gone by on planet Earth. So this is part and parcel of how the world is constructed. Now, when it comes to the intuition that this type of meandering through time would be possible, because after all, as you say, it's just a path, and paths you can meander in any direction, is this something which effectively all cultures have come to as something that matters, that's important, that they would focus attention on? Or are there cultures for whom it's just so irrelevant that it would never even come up because it's just not something they would care about?
Well, some people argue that the idea of time travel, as you described it, or the way that it happens in science fiction, is actually a relatively new idea, that it happens with the machine age, with the industrial age. and true examples of really going to another place in time don't start happening in narratives around the world until then.
You mean because we couldn't travel far? Is that sort of what it comes down to?
People have various arguments. There's certainly lots of interesting time distortions that happen in traditional narratives. So, for example, in the Ramayana story, you can have all the roosters start crowing earlier than normal to make the day come sooner because you don't want the prince to finish all of the castles that you've assigned him to build because otherwise you'll have to marry him, things like that, you know.
Right.
So there is a time distortion you can create through more traditional means.
Right.
So you can think of that as a kind of time travel. It's not maybe strictly the same kind of idea as you were talking about.
But are there, I mean, either cultures or perhaps even neurological maladies that focus on the present in a manner that just sort of makes the past and the future not something that's vital to that individual's existence?
There's this fascinating book by Daniel Everett about Don't Sleep, There Are Snakes, and he studies a population of indigenous to the Amazon in which he claims that they're very present biased. So that they don't have good words for the long-term future, deep time, deep future, deep past. So, but nobody would call that a neurological bias. But the interesting part there is, so they use tools, but they don't, for example, often, and it would frustrate him because he would lend them their tools, they wouldn't store them. So they wouldn't say, okay, I'm going to need this tomorrow. And when you think about one of the biggest technological achievements we've had, we talk about, okay, carving a obsidian blade, carving a knife out of an obsidian blade. That's part of the story, right? The other part of the story is saying, I'm going to use this blade. I'm going to store this blade because I'm going to use it for this. So that requires the time travel. Now, in relation, but that, it was strange, and this is what Lera was referring to. True time travel, in the sense of going to the past and jumping back and forth, only emerged, apparently, in the literature, mostly in the late 1800s. There was a couple of stories about time distortion, but true time travel, jumping back and forth, a la the Time Machine. Why did it take so long, in a way? So you look at Shakespeare, you look at the Bible, you look at all these stories.
We look at so many very creative mythologies, which, talking about language's capacity to mix and match, there are so many entities that are not in the real world, but are some linguistic mashup of things that are in the real world. It doesn't seem like it'd be that hard to put time into the mix in a way that would yield all sorts of time travel stories going all the way back.
And why didn't we?
Yeah, why didn't we?
Well, you know, there are ideas about time in cultures around the world that are hard to express in English and also hard to understand when you're not from those cultures.
Yeah.
And so I can try to tell you about one, and it'll probably make as much sense as it does to me if I do it. So I'll try. In some Aboriginal cultures in Australia, there's a belief that things don't really change, that time isn't really passing, in a sense, that when you're born, you are really a new version of an ancestor that you had, and so that ancestor is getting to relive their life. But also there's this other realm that is the ancestor realm, or it's called dream time sometimes. And so everything continues in that dream time outside of time. Now, I don't know what I just said. Right, I can't tell you that I have that I can take the words that I just used and put it into my understanding of how time works. But I believe that the people there have some representation that makes sense, and I haven't reached it yet, right? And so I think we don't fully know the range of possibilities for thinking about time, because it's hard to go in and really wrap your mind around someone else's understanding in the same way that you have to intensively train your undergrads to get them to wrap their mind around relativity, for example.
Yeah.
It takes a lot of training into that system.
So speaking of time, we're starting to run a little low on time, but do jump in if you had another thought, because I had one final question, but go first.
I was just going to say, in terms of it is still strange about why it took us so long for time travel to appear in fiction. But as you know, the end of the 18th century was a very dynamic period, both scientifically and in literature. And it was sort of the time where people like Einstein and Poincaré were beginning to think about time more deeply. But some people have made maybe what was the critical event that set the stage or planted the seed for time travel was actually the emergence of photography. And the ability to store something. That was the first time you could have faithful reproductions of something in the past, in the sense that made it still exist. And maybe that allowed us to start creating stories of going back and visiting that. But it is a mystery, and it's strange that there's so much stories in literature where the same themes are hit upon time and time again, but time travel was really slow to emerge.
So one final question that sort of relates to that as well. You know, we often, I think, look at ourselves as blessed by the capacity to think about the past and imagine the future. I mean, it opens up our world in a way that makes us human, right? If there's language certainly makes us human, but this capacity to be able to freely roam the timeline in our minds is something that is really iconic to our species, as far as we can tell. At the same time, it also creates a great deal of anxiety, a great deal of pain and suffering. I mean, mindfulness teachers throughout the ages have focused us on living in the moment as opposed to this capacity. So do you find that that's a curious tension? I mean, how does one deal with that tension? I mean, from the neurological standpoint and from the cognitive science standpoint, any advice on how to deal with that tension between those two capacities?
Want to go first?
Sure. I think in general, being reminded of how small you are relative to the scale of universe, whether it's in size or in age, is useful. When you're concerned about small things, maybe someone said something annoying in a meeting that you had, in a staff meeting, just think about how many millions of years the Earth has existed, and it'll seem like a small speck.
Yeah, I got to tell you, in 2016, the most hopeful thought I had was 4 years to 2020 and 13.8 billion years since the Big Bang, so everything's going to be just fine.
Yeah. Any kind of perspective. Yeah.
I think that the part of the answer to that question is our ability to think about time is itself dynamic, and it's true that our ability to think about the future and think about the stresses that are arising or what we should have done differently in the past is a major source of anxiety. The alternative is just to be like your dog, I think, is like my dog, is very focused on the present. So the thing is that in this Amazonian tribe that doesn't think much about the future, the author of the book is pointing out, yes, they seem to have less anxiety, but they also have less time to live.
Meaning?
Their mortality, their lifespan is shorter because they don't think about the future. So there's a bit of a catch-22 here, right? It's our ability to think about the future, which causes anxiety, which sort of assures that we have a future. But clearly we have to have a middle ground in which, and part of this is, there's nothing wrong with being present in the moment while you think about the future, right? So, and as scientists, you have to do this, where you focusing on a problem that you want to resolve sometime in the future. So I think it doesn't take away anything from the notion of living in the moment or mindfulness. I think that's incredibly valid approach. But the lesson isn't that we should ignore the future. And this is the problem that we're all struggling with, is we want to ensure that our relatives and our offspring have a future,
Yep.
so we still have to worry about it.
Absolutely.
When you asked earlier if there are any neurological conditions or groups of people who are very present-focused, probably the most present-focused are crack addicts.
Yeah.
I didn't think that's where you're going.
But that is a group of people who have a very, very narrow time horizon that they're focused on. So you can see there are also downfalls of extreme present focus.
So the balance, I think, ultimately is the way of going about it. Well, thank you both very much for joining us. Please join me in thanking. Thank you.
Thank you.
Excellent conversation. Thank you.